Hey everyone, my name is Lin Han. I'm the Principal of Community and Education here at Hyperganic, and today I'm going to walk you through how to set up your first project on HyDesign. Let's go. So diving into the Hyperganic platform here, we can launch HyDesign in two ways. We have the button over here under Available Apps, or we could go to the HyDesign banner. After we launch HyDesign, we are greeted with this projects page where we can create projects, share projects, as well as view our own projects, including the deleted one. So now let's go ahead and create our first project, and we're just going to name it Intro Project. Now we are required to add a description, so let's add my first project, and we click Create Project. On this screen is where we will design the objects. You can see all the functions that are neatly placed in the ribbon up top. We can see also the viewport in which the objects that we design will appear. We can also see some icons on the top right corner of the viewport, and that's there to help us view the objects that we design in different ways. Now to the right, we can see a panel called HyDesign Objects and Modifiers, and that's where all the objects that we create, as well as the modifier functions that we use to modify the objects, will be shown. So now let's create an object together and cover most of the functions that you will be able to use in HyDesign. Now typically you can go to Menu and import an STL or OBJ file of your model and then work with that. But you also can start with some primitives. We have cube or cuboid, we have cylinder, and we have torus. So for this example, let's use the torus primitive. So let's go to primitives and create torus. Let's set the radius to 15 and 5 and hit confirm. And you can see that the torus appeared in our viewport. Now here is where we can introduce some of the functions to control the viewport. We can scroll to zoom in and out. We can left click and drag to rotate about the object. We can also right click and drag to pan. And now let's click here to bring the object back into the center of the viewport. We can also go into full screen mode where the function ribbon will disappear. We can also have different perspectives, so from top, bottom, left, right, front and back, as well as engage the isometric mode. So with this isometric mode engaged, we can very clearly see the dimensions of the object. Each square over here represents 10 millimeters. And because earlier we said that the torus radius is supposed to be 15, there's exactly 1.5 units from the center of the tube to the origin point. So that's 15 millimeters. And we can also see that the tube radius is indeed 5 millimeters because it occupies the length of 1 unit square. We can also view the object in a split plane mode using the final button that is on the top right hand corner of the viewport. Let's go into X positive split plane. From this direction, we can drag the slider to see different cross sections of the object. Now let's use the rotate function to rotate the torus 90 degrees about X. Let's now select the object to rotate, which is the torus. And because the rotate function only rotates objects 90 degrees, here to rotate the torus 90 degrees, we will have put 1 there. And let's confirm. And there we go. So now let's go ahead and create yet another torus. So go to primitives, click torus, and it's going to be the same in terms of dimensions as the first one, and confirm. You can see that the second torus is rendered in black, but if we want to change the color, we can always click on the icon to the left of the view button, the I button, click on the color panel and select whichever color you want. Or you can also key in specific RGB values of the color that you want to render the object in, hit enter, and then click save. And then you can see the object rendered in the desired color. To change the name of the object, simply right click, edit the name, and hit enter to save it. So in this case, we name it torus2. Now let's use the translate function to move torus2 in the X positive direction by 30 millimeters, and we hit OK. Next, let's use the Boolean function to merge them into one object. In this case, the main object will be torus and secondary object will be torus2. And the Boolean operations include other functions, but for now we're going to use union and hit confirm. Now you can see that they've been unioned together. They're in the same color. And in the objects and modifiers panel, you can see that the main object torus is the only object there. Next, let's use the shell function to create a 2mm shell of this shape. So main object is torus, because over here you can see torus is the only object. And the direction of the shell will be inside to maintain the overall dimension of the object. And thickness, let's set it to 2 mm and hit confirm. And right now the shell has been created, and of course it looks the same from the outside. But if we go into the split plane mode, you can actually see that this object has been shelled, and the shell has a uniform thickness of 2 mm. Now that I've union and shelled the object, let's move this entire object into the center by using the center function, which has only one input, which is main object. We'll select torus here and hit confirm. And once it's centered, you will realize that the object not only moved towards the center in terms of X and Y, but along the Z-axis as well, it's been brought up to the build plane. So now let's try to infill this shell with a triply periodic minimal surface, or TPMS. So the inputs for this primary pattern for TPMS here is a density, and this is the object basically. And we need to select torus and set the wall thickness to 1. Let's leave the rest of the input as default. If you'd like to know more about these inputs, please refer to the HyDesign documentation. So the next compulsory input that we will need to set is the cell size. Let's set it to 5 mm in each direction and hit confirm. And once that is done, you can see really quickly that the shell itself has been filled with a gyroid pattern. And we can slice it in the X positive direction to confirm that this is still the shell. Let's close it up. The other highlight of HyDesign is that you can morph between different TPMS patterns within the volume of one object itself. So now let's try to add a pattern to this gyroid filled shell. So now let's click on add pattern. For select infill, we will select torus, which has already been filled with the gyroid implicit pattern. For transition start and end, it really depends on the morphing direction, because transition start represents where it will be 100% gyroid at the start of the object, and the transition end will represent where it will be 100% of the second pattern that we choose at the end of the length of an object. So in this case, let's select 0.1 for transition start and 0.9 for transition end. At the second pattern will be shorts P. Let's leave the morphing direction to its default, which is along the X-axis, and confirm. Now here you can see that the morphing has successfully taken place. And because the morphing direction is in the X positive direction, towards the right of this object, it will be gyroid, completely gyroid. And towards the left, further out along the X-axis, it will be shorts P. Alright, so maybe let's try another pattern. Let's try shorts D and confirm. Now we have yet another example of how HyDesign morphs various TPMS patterns from one to another. But that's not all, we can also modulate this pattern. Now in HyDesign, you can modulate TPMS infilled objects in two ways. Number one is the cell size modulation, and number two is the wall thickness modulation. We will cover both, but we will start with the cell size modulation. So now let's select infill torus again. And for cell size modulation direction, let's keep it to its default, which is the X positive direction. Now the grading factor is a ratio of how many cells of the TPMS pattern we can fit at transition start versus transition end. If my transition start is 0 and my transition end is at 1, with a grading factor of 2, I can fit twice as many cells at the end of the length. Now let's try with a grading factor of 0.5. maintaining the wall thickness grading factor to 1. Now you can see that towards the end of the length of the object along the X positive direction, the cell sizes are more sparse. You can see that the cell sizes increased almost 2 times. So now let's see what happens when we modulate the wall thickness. So instead of having a grading factor of 1, now let's set the grading factor of the wall thickness to 0.5 with transition start and end at 0 and 1 respectively. And you can see that towards the end of the object along the X positive direction, the wall thickness has been reduced by half. Let's use the split plane view in the X positive direction to have a look at how the thickness changes along the object. Now let's have a look at beam-based lattices, and for that let's create a new primitive cylinder, and let's set it to a radius of 15 mm and a height of 30. Confirm. And if you remember from earlier, we can change the color of the object by keying in specific RGB data. Hit enter and save. Now we have a blue cylinder. Now let's click on lattice fill. Within the lattice fill function, we have inbuilt several beam-based lattice unit cells. Let's select diamond for now, and we want the lattice object to be the cylinder with a beam thickness of 0.5 millimeters and a scale of 0.5. For anti-alias, let's leave it as default. Now let's hit confirm, and you can see that we've infilled the cylinder with the diamond unit cell. Let's try with another unit cell. Let's say hexagon, and confirm. Now we have a cylinder infilled with the hexagon unit cell. And if you realize, we have one more function called BASF forward AM lattice. Let me show you that, but before that, let's hide the custom lattice, and let's click on BASF forward AM lattice. For the main object, it's going to be still the cylinder, and we can see that there are multiple inputs over here, including a modulation map, the material, lattice pad, code, and stiffness number. We do not see the lattice beam thickness as well as the unit cell size and scale. And the reason for that is because we've developed lattice test pads that have already validated all these lattice unit cell designs at specific scale and thicknesses for various use cases. For example, for the material UltraSynth TPU01, we have developed some lattices already for footwear. Within the lattice test pad, we have various code that represents various scales of the lattice, as well as stiffness number to represent different beam thicknesses. And you can see that this is the validated lattice for footwear. And if you have one of the UltraSynth 3D lattice test pads, you can actually get tactile feedback from the test pads before designing for your use case, be it footwear, protection, or seating. And if you're ready at any point in time to export your object, simply go to Menu, Export. For the node, this is the object itself. Export type, we have several file formats there for you to choose from. And give it a file name and you'll be able to export it now. Now in this open access public beta, exports are free. So once your files are ready to be downloaded, you will see a notification at the top right corner. You could also gain access to previous notifications and exports by clicking the bell icon at the top right hand corner in case you need to re-download or have a look at the previous exports you've made. So that's it for the basic walkthrough for HyDesign for this open beta. More functions will be on its way, and if you have any questions, feel free to reach out to our team and we'll be there to help you. Thank you.